Hello. Um, so I don't make videos, but I was having a lot of trouble understanding the um, attention mechanism in the Google paper, Attention is All You Need. And I came across a post recently that was using transformers for forecasting time series data. And I wanted to try to rebuild that from scratch, but also just using basic attention and seeing how that would work out. And I dealt with a lot of frustration trying to get there. And so I wanted to create a video that showed how this works and highlight some of the points that I had a lot of trouble with. And so I have the paper up, Attention is All You Need. And here is our scaled dot product attention that we'll be using to forecast a time series. And you'll see that when Google wrote this paper, they did it from kind of a search engine perspective. The original idea of the transformer was essentially for translation. Um, and when you're doing a search engine type problem, you have a query, a key, and a value. And so they based the architecture on that. And so the queries and keys come into the model through one path, and the value, which in a translation problem might be different, but for our purposes will not be different, um, comes around through a different pathway essentially. And so that's all kind of gibberish, but to make it a little more clear, um, for our purposes, our time series will be the same query, key, and value. And so in this paper, originally, the queries, keys, and values are matrices. And there's a reason for that in language processing. But for time series prediction, we don't really need it to be a matrix. It can just be a vector. And so I have this other post up here for a little bit of context on that. Um, this Stack Overflow post by Raylined is really helpful. It's how I finally made sense of this all. The key and value matrices are supposed to be the length of your sequence, for us, a time series, multiplied by an embedding dimension. And so in natural language processing, you embed the words and or sentences that you're processing so that they can be computer readable as vectors of some dimension. And those vectors are typically float valued, but with quantization, they become integer valued, etc. But for a time series, you already have a float valued vector. Um, and so um, it might be a theoretical question whether or not you should or could embed that, but for the purposes of our very basic example, we're not going to embed that vector. So we'll only have a sequence length, and this embedding dimension will actually just be 1. So we'll just have essentially a vector. But it is a vector of sequence length times 1 because the intention mechanism is shown here in the post, where we have our queries and our keys. It's actually highlighted in this comment that this should be queries keys transpose instead of queries transpose keys. But we essentially multiply these matrices together, one of them transposed to get a full matrix, and then we softmax that and multiply that by the values. And so that's the technical side of attention. We will just be using attention without the full transformer mechanism, but the idea behind attention was that you'd have these input matrices and you'd output essentially a vector of probabilities that could be used to select your next word, because in natural language processing, you're looking for sentence continuation, especially for chat models, large language models. You're looking for probabilities of what the next word should be. But there are ways to get regression value out. So in the actual transformer model, After the attention mechanism, you go through this feed forward portion, and as shown here, you can softmax into output probabilities, or you could just feed forward into like a regression problem. And so the idea that we'll be using today will be an attention layer into a feed forward into a linear output used for regression. All right, so having discussed the attention is all you need paper and the attention mechanism, here's some code that implements the attention equation using vanilla PyTorch and NumPy. PyTorch actually has its own implementation of the transformer model as a whole, which I'd highly recommend checking out, especially if you're trying to do language prediction or sequence prediction. You can use specifically the transformer encoder portion of their model. But as a basic introduction to just understanding attention a little better, or if you have low data or need something very simple, here's a way that attention can just be applied from scratch. And so to start out, I've extended a torch module to build just the attention portion of our model. And so I'm using linear neural network layers here for the queries, keys, and values. This, in our problem, represents the weight matrices that are learned for queries, keys, and values. If I hop back to the attention is all you need paper, we'll see in the multi-head attention portion, they describe the parameter matrices that are applied to the queries, keys, and values coming into the model. And this is really what's being learned in a transformer model, are these parameter matrices for the attention components, the queries, keys, and values. And so if you look into large language models in more detail, especially adapters, you'll see that these matrices of parameters are of a lot of interest in current research, especially optimizations that can leverage these massive models like GPT-4 while only adjusting some of these matrices without, looking at the whole model. And so, but instead of these, since our embedding dimension is 1, and we're just looking at a sequence, we can actually just use linear neural network layers. And so these linear layers are applied, and then the attention mechanism is implemented in the standard fashion. Queries times keys transposed. I apply a lower triangular mask. This just basically hides future values from the current values so that the model only learns a sequence based on the previous values in the sequence without being able to look at future values. More details on mask can be found in the paper and online and on Stack Overflow, but this just hides future values in terms of prediction. And then softmax is applied to the queries, keys pathway, and then that is multiplied by the values. And so this is just the exact attention equation as shown in the paper implemented into a class. In order to use this, we have to apply a additional feed-forward network layer to the output of the attention mechanism. And so that is accomplished through this additional class, which takes the attention class and applies a series of linear layers with ReLU activation in a typical neural network fashion. And so this just takes our attention and converts it into a regression problem. And so having defined a model, we can create a data set to apply that model to. And for our time series problem, I've created this sequence of noisy sine wave data just as an example of how this attention mechanism performs with a simple problem, but but also one that's very nonlinear. Um, and so this data is then chunked into a data set where sequences of length 200 out of the 1,000 data points are used as our input values, and y values of the next data point are predicted. And so the first data point in our x values is data points 1 through 200, and our first y value is data point 201. And that is segmented across the entire range of data to create 800 observations of size 200. And so, so we create our data set, and then we train the model on this data. And so in practice, you'd want to do some sort of hyperparameter tuning to find the right number of epochs, maybe apply early stopping, model checkpointing, appropriate batch size, learning rate. Some other parameters aren't shown here, maybe like the model size and model architecture might be of interest. I just kind of spitballed it and found a series of parameters that worked well. But this is just for the sake of showing this off without really getting to the details of ML ops, etc. And so I found that actually 20 epochs is good for this specific problem. I actually trained it longer and it started to fall apart, and so I found that 20 was a decent stopping point. And so we have 1,000 time series data points that we use to train the model, and then we will forecast the next 1,000 data points. And we'll do that by taking the previous chunk of data in the sequence and predicting the next value, and then appending it to the sequence and just iterating over that 1,000 times. And so we do this prediction loop. And so we've predicted the next 1,000 data points, and then I will replot that data that we saw previously, the first 1,000 data points, and then at the end of that data I will plot our predictions in red, and then an actual sine wave continued, the actual values continued in green. And so here's that plot, and I'll maximize this so that we can just see it in detail. Not perfect, not 100% perfect. The noise in the original data obviously adds some difficulty to the problem, but it looks very good. It doesn't look too bad, especially considering that our forecasting was based on iterative forecasts and then predicting off of those data points. And so we see the amplitude, especially on the bottom, getting further and further from the accurate amplitude of the sine wave. But the top looks kind of good. And so, yeah, so it's not horrible. It could be improved, certainly, by doing all those things I mentioned before, like finding the correct hyperparameters and some more rigor in terms of building the model. But yeah, that is essentially how you can use basic attention to forecast a time series, and I'll link the code in the comments so that you can study it or use it if you want. And thank you very much for listening, and that's all I have today. Thank you.